Log on, tune in, find out. Another good idea from Cambridge.
Peter from the University of Augsburg in Germany who talk about elasticity.
Thanks. Well, thanks a lot for the introduction and the opportunity to speak here today. So I'll report on some joint work with Mike Mayland from the University of Auckland. And the main things that I'll be presenting are based on a recent paper. So if you're interested, I'm happy to pass that on to you after my talk. So what I'll be talking about is the generalized eigenfunction expansion. And so my talk will be quite focused on this method, and the idea of the talk is really to advertise the method as a method to solve time-dependent scattering problems, linear scattering problems on unbounded domains. And it's one of the examples where there is an analytical method which has had some attention, not too much though, it dates back to the 1950s, but hasn't been explored too much until very recently. And but it's only been explored from a quite purely analytical point of view, and I want to show you that it can also be used to as a simulation technique. And it is quite general. As I said, I think it can probably be applied to most problems of linear scattering on unbounded domains. And because the Fourier domain type approach, there's no time stepping necessary, and basically the main computational effort is in solving time harmonic problems. So we've seen quite a few talks on solving time harmonic problems, so the idea really is that you can use your favorite method to do that. And so I'm sort of, for the application I'm thinking of, and I'll show you that on the next slide, comes from water waves, and there in particular people have spent decades and decades to come up with efficient solvers for solving time harmonic problems, because that's what engineers are mainly interested in. So you can use those. And what's also quite neat, and this is sort of more again from an analytic point of view, but it's also useful for coming up with some results, is that a way of approximating near resonant behavior directly comes with a method. And so as I said, the aim of the talk is to sort of advertise the method and to use a simple but not too trivial test problem to explore the properties. So the test problem, of course, I have to talk about a bit so you see what's going on. And what I'll be talking about is two-dimensional linear water wave scattering by a vertical elastic thin plate. So the basically picture looks like this. So now where's there? It looks like this. So it's two-dimensional. The domain extends all the way to infinity in this direction, and there's a vertical elastic plate here bounding the domain, which you can think of as a very simple model for some elastic tank wall, if you like. But the reason why I'm considering this model is really that as at least as far as I know, it's the first time that there is sort of a more complicated scatterer than just something with a Neumann condition, something just rigid. And also the domain is semi-infinite. So far it's only been used for infinite domains. So basically if you want to think of the 2D case where the domain also extends to infinity in this direction. And so I'll be talking about linear water waves. The fluid dynamics concerns linearized, incompressible, inviscid, irrotational flow under gravity. So it's usually termed surface gravity waves. And the problem, as you'll see on the next slide, is formulated in terms of an acceleration potential. So those of you who are familiar with these type of linear fluid problems are probably quite used to working with velocity potentials, but it turns out for the abstract formulation that I'll need later on, it's much more convenient to work with an acceleration potential. And so I want to stress, though, that the idea of the method is not constrained to this particular problem at all. And there has been some work on three-dimensional Helmholtz scattering, and you can also look at other related problems of linear scattering, for example, acoustic scattering, or actually the very original paper was for Schrödinger equation, so it is quite a general method. So let's talk about the test problem a bit more, so you see what's going on. So this is my domain. I have a rigid bottom. I have the plate here, and I have this semi-infinite domain of water. The unknowns that I'm interested in are the water surface displacement from the position at rest, the plate displacement, and the water acceleration potential. And the equations of motion are as follows. They're here in dimensionless form. In the water, due to this is basically the continuity equation tells you that the acceleration potential has to be harmonic function. And then for the plate, you take the linear plate equation where there's a forcing at the wetted plate, so z equals 0 is the still water surface, and there's no forcing where the plate extends beyond the water. Then there are these coupling conditions, coupling the accelerations. There's the other free surface condition coming from Bernoulli's equation, so this is the free water surface, conservation of momentum. And at the bottom there's no flux condition. I have edge conditions for the plate. I'll talk about those in a second. I have a radiation condition to minus infinity. And of course, most importantly, because I want to solve the time-dependent problem in the end, I have to satisfy initial conditions. And that's really, the key point, as we'll see later on. So the problem for the plate is this beam equation. I introduced here the characteristic function of the wetted plate. So it's just 1 underneath the water surface and 0 above. And I'll consider the following boundary condition. I consider the plate to be fixed at the bottom, and it's either fixed or free to move at the top. That's, I think, two reasonable boundary conditions. What's really important is, though you can use other ones, is that the fourth order derivative subject to the boundary conditions you use is self-adjoint, so you can expand your plate displacement in terms of the corresponding eigenfunctions. So this is for this particular problem. This doesn't have to do anything with the generalized eigenfunction method, though. So this is just my solution, so my way of solving this time harmonic problem. So let's look at the time harmonic problem. You factor out the an exponential, a complex exponential. You look at complex potential, complex water surface displacement, and I didn't, because there was no space, I didn't put the same equation for the plate displacement. But what you do is, this is quite well known, because we have the simple two-dimensional problem on a rectangular domain. You can expand your acceleration potential in these eigenfunctions. That's basically, these are the vertical eigenfunctions accounting for the free surface condition. You have this dispersion relation, because water waves in finite depth are dispersive waves, and this dispersion relation has one purely imaginary root here, which corresponds to the propagating waves, one going one way, one going the other, and then you have an infinite set of evanescent modes, so basically modes decaying away from the scattering. And so now you've expressed your all you need to know on these coefficients Cm, and now you can come up with a system of equations. I'm not going to go through the details. It's quite a simple calculation. What is important, and this is what I want to stress, is that in the end what you come up with is a linear system of equations for your unknowns. So if you all do it like this, it's an infinite dimensional system. You can truncate and solve this problem. And the problem that you got to solve has the structure, and that you have the identity, then some perturbation which comes from the presence of the scatterer, and this is the operator you have to invert in order to find your unknown coefficients. This comes from the forcing from the incident wave. And the point being that this operator here depends on the wave number, right? So basically, for a given wave number frequency for the time harmonic problem, you have to solve this problem where you have to invert this type of operator. For this very simple problem with the vertical elastic plate, the matrix elements here can be calculated analytically. It's all very nice. If you have a different problem, more complicated, some scattering from some nastily shaped obstacle, then the whole system might look very different. But in the end, what you have to solve is a linear problem like this with a dependence on the wave number. All right, so this is how I solve this particular time harmonic problem. As I said, if you have a different one, then use a different method. That's fine. What I wanted to aim at, and this is where the generalized eigenfunction expansion comes in. Actually, I'll show you some pictures just so you see what it looks like and that it all works. So this is the, see that? Yeah. So this is the what you see if the plate's just free to move at the top, and you send in time harmonic waves, and what you see is a standing wave pattern. This is not surprising at all, and this is the same picture that you see if the plate's fixed at the top. I just want to emphasize that these are quite large waves. Of course, it's linear theory, so so you should think of much smaller waves, but it's blown up, so you see what's going on. But the point being is that I want to solve the time-dependent problem. So basically, now the standard thing is if I know how to solve time harmonic problems, then the question is how can I superimpose time harmonic solutions what I need, how do I need to superimpose them? I need to superimpose them such that I meet my initial conditions. In this particular problem, the initial conditions that I want to meet are the initial water surface displacement, water surface velocity, and initial plate displacement and plate velocity. And so the question is, how do I do that? Well, and just generally, it's well known. What do I have to do? I need to find these functions f1 and f2. These are the time harmonic solutions. From now on, I'll always denote them with a hat and the explicit dependence on the wave number. And basically, I multiply with cos or sine, I integrate, and that's what I get. So the question is, how do I choose f1 and f2 in order to meet the initial conditions? Just want to point out, you could also work with complex exponentials here instead of cos and sine. Doesn't make a great difference. It both has advantages and disadvantages. Okay, so the question is, what do I need to do? And this is where the general theory comes in. I need to restate the problem in terms of this abstract wave equation. And basically, what these things are, these are directly to Neumann type operators telling me what the problem is. So basically, the A11 tells me for a given water surface displacement, what is the acceleration of the water surface? Or for A21 for a given water surface displacement, what is the acceleration of the plate? And it becomes slightly complicated then if the plate extends beyond the fluid domain, because you don't have this full coupling. You have to extend the whole thing a bit. I don't want to go through all the details, but the point being is that you can rewrite your problem in this form. And then what you got to work with is this operator here, which I call A, and this is basically where all the analysis is hidden. Is that this operator is self-adjoint in its domain equipped with this special inner product, which basically represents the energy in the system. So this is the L2 inner product of the water surface displacement, and here you have beta times the L2 inner product of the second derivatives of the plate displacement. And if you take the domain of that operator and equipped with this inner product, you see that it has a continuous spectrum, just a positive, non-negative real line, and the corresponding generalized eigenfunctions are precisely the single frequency solutions, so the time harmonic solutions that you calculate anyway. And now, this is very useful information and quite a complicated derivation. Is that if you take inner products, like in the special energy inner products of single frequency solutions with respect to different wave numbers, they normalize in this way. Okay, so there are quite a few assumptions hidden here as well, but I don't want to go into all the details. So this is what we know. We know we can write it like this. And now the question is, so again, how do I choose f1 and f2 in order to meet the initial conditions? So well, what do I do? All right, well, if I plug in 0 here and I want to meet the initial conditions Z0 and W0 as the initial displacements, well, then I do the same on the right-hand side here. The sine term vanishes, cos with the t here is always 1, so this is what I'm left with. And now what do I do? Now knowing those properties of the operator, it becomes quite a simple calculation. I take inner products with respect to the special energy inner product. This is just spelled out, so just from the definition of the previous slide. And if I use this normalizing condition from the previous slide, I get these inner products of eigenfunctions of different with different wave numbers. So I calculate this, and now I have an explicit expression for f1, because these are just inner products, L2 inner products of known things. So this is just spelled out with the like those L2 inner products just explicitly spelled out. And I can do the same for initial velocities, just the same type of calculation, and you get this explicit expression for f1 and f2. This is all very nice. Basically, you're done here. I want to show you two more things. One is just how things simplify and how you can recover well-known sort of engineering tricks, and also this near resonant behavior I wanted to talk about a bit more. So in particular, let's look at a slightly simpler case. Well, if you only have initial displacements and the initial velocities are 0, so this is 0 and that's 0, then F2 is 0, and the formula simplifies, so you're just left with this, and you can, I mentioned that before, you can express everything in complex exponentials, so this is what you get. And let's look at an example where you have an initial water surface displacement at naught, and you have everything, all the other initial conditions are 0, so we already know F2 is 0. I plug this in. This is explicitly spelled out, the single frequency solution. And now I can make what is quite typical in engineering applications is that you have what you're interested in is what if you have a pulse wave and you sort of which travels towards the scattera, what's going to happen? So basically the initial water surface displacement is 0 near the scattera, and if I do that, then I can neglect the evanescent waves here. I'm left with this simple expression, and it basically actually turns out that you can rewrite the formula from the previous slide with this F1 as this thing here, where you just take the Fourier transform of your initial water surface displacement and you stick it into this formula here. And this is actually quite well known to engineers that you can do that. This is basically that you can just take the Fourier transform here and stick it into this formula, but it drops out as a special case of this theory. So I can show you some pictures, what it looks like. So again, these are sort of in amplitude quite exaggerated, but you can see that the wave splits and you can and it hits the plate. You can see some oscillations, and eventually it all radiates away to infinity. So what you can do the same for initial plate displacement. The derivation is slightly more messy, but not really. And you see pictures like this. So this is you bend the plate, you let it go. You can sort of see one long wave traveling away, a few oscillations here, but that's it. And if you look at this particular situation, you get a behavior like this. And this of course happens for very specially chosen parameters of stiffness and mass of the plate. Well, what you see here is that you have this ongoing oscillation. Right? So it's basically everything's flat, you let go, and you get this ongoing oscillation. And the question now, of course, is how can you approximate this highly oscillatory behavior? This is not a resonance, I'd like to stress. The amplitude here decays over time, so there is energy radiating away to infinity, but very, very slowly. So the question is how can you approximate that? And the first thing you notice is, where does it come from? It comes, of course, from this function f1 that you've got to stick into your formulas for where you superimpose the single frequency solutions, and you see it's got a sharp spike here at a certain wave number, and I don't know, it's like 11.6 or whatever in this particular case. And of course, what that corresponds to is precisely the wave number of this highly oscillatory wave that you saw before. And the question is, so where does it come from? And it comes from the following. This is the operator you have to solve for the single frequency solutions, right? And the thing is, this operator is for a given wave number. It should always be invertible. That's the idea. If the wave number is real. I mean, you're only interested in real wave numbers normally. But the point is, this thing that you saw before happens if you have a k here, which I could then call kr, which is complex but with small imaginary part for which this thing becomes singular. So this is not a real k for which it becomes singular. Then you'd have a real eigenvalue, and problem would be then you had a real resonance. But this is I call this complex scattering wave, and we've seen this before in a talk yesterday, I think, under a slightly different name. But so this is quite well known that these things can happen. And what you can do now is you can approximate the solution, or like the inverse of this applied to your right-hand side, just by simple expansion. You can calculate what these alpha r and cr are, and well, you can make this very, very nice computation. So you say, okay, what I'm interested in is this thing here. So we do this for incident wave from far away again. So the simple situations, the formulas become a lot simpler. And you're interested in long-time behavior. So you're wondering what happens for large t. And so basically what you do is you take your formula, you say, well, if I send in an incident wave, I'll wait long enough, and then the incident wave will disappear, so you leave that away straight away. And now what you do is you insert this approximation from the previous slide, where you have this wave number close, this complex scattering wave number close to the real axis. And then here you have an integral over the non-negative real line. What do? You close the contour on the lower half plane, and there's this pole, this one precisely here. The contribution from the additional contour of integration, that will decay quickly because of this exponential term here. So so if t is large, the error that you make is very small. But now you have a closed contour, you have a pole, and you can use the residue theorem, and you calculate the residue, and this is what you get. So it's a very simple expression here, where you just have these sums, no more integration, and you just pick up this one residue. And you can do the same as I have if you have initial plate displacement, or for the general formula. It just becomes slightly more complicated, which is why I didn't want to show it. So what we're interested in is approximating this behavior here. And, well, now I hope you believe me so far that this comes from a complex scattering frequency. So what I want to show you now is the time over time, the behavior, or the surface displacement over sit at the point -4 here. And this is what you see here. This is, well, exact solution means you use the full computation. And you see that after transient time, you get precisely this behavior that we've seen in the animation. And if you use this simple formula coming from the closing the contour and picking up the residue, then this is the picture that you get. And you see that after some time, the approximation is really, really good. And you also see that the amplitude decreases, so there's really a near resonance, because it has the complex scattering, because it has an imaginary part. And this is why you see that behavior. So to summarize, I showed you how the generalized eigenfunction expansion method can be used as a general method for solving time-dependent linear scattering problems in unbounded domains. Basically, what you have to do is you have to find what this abstract operator is for your problem, and you have to find this energy inner product corresponding to your problem, and you have to find out what how the eigenfunctions, the generalized eigenfunctions, normalize. And of course, there's a lot of analysis behind that, but this is basically the path. And then I also showed you how you can approximate long-time behavior with these formulas that you end up with, making use of these complex scattering frequencies. And I applied the problem to this very particular test problem for a semi-infinite water domain, a vertical elastic plate. But as I said, I'm quite sure that the method can very likely be used for quite different problems, and for problems where you also use different methods of solving the time harmonic problem, because it really doesn't depend on that. Okay. Thank you very much for your attention.
Any question?
Expanding a function as a linear combination of eigenfunctions of a differential operator is what is known as the Birkhoff approximation.
Okay.
And there are some results, and without using various tricks, there is a theorem, I believe, of Keldysh that says that if you are taking the first n eigenfunctions, say in 1D, the convergence is like 1 over n. In more dimensions, you need to use the Weil theorem, but it is quite similar. One can accelerate it, but not trivially. But essentially, it means that you have quite poor convergence, which probably might not matter for water wave problems, because you don't need very high precision. But in general, this can be.
Yeah.
There are ways of taking care of it, but they are non-trivial.
Okay, no, thanks for that. Yeah, well, to comment on that, for the water waves, also you're usually interested in low frequencies and that sort of stuff. So yes, but although higher frequencies become more important in certain applications as well. But I'd like to get back to you on those things. Thanks.
Concerning your KR giving rise to the approximate resonance, is there some limit in which it becomes real? I mean, I am trying to understand whether there is a physical way of understanding your phenomenon.
If it becomes real, then you really have a real resonance. And this of course also goes with uniqueness of the problem, which is still quite unsolved even for linear water wave problems, like the four theory. So this becomes quite involved. The thing is that it's actually the assumption for this thing to work that there is no real eigenvalue, and we haven't observed any. But if you have special structures, you can observe basically trapping of waves, and in that you'd have a real eigenvalue. So in all the cases for this particular problem that we've observed, you get close to the real axis, but you never hit it. But this is a very important point.
Could you extend your method to deal with situations where you have an arbitrary force field acting on either the wall or a wind field acting on the surface? Because you just give the initial data.
Yes. Well, I mean, if you have some
time-dependent forces acting on it.
But if you mean like if you have some pressure field on the surface
field
or something like
something
that,
acting on the wall.
okay, that would enter the boundary conditions. So as long as it's linear, but it would be time dependent. Is that
It
what
would be
you're saying?
time dependent, yes.
Okay, I have to think about that. Thanks.
I have a last question. Can you compare in the same direction the computational cost to some problems where you solve the time-dependent equation directly?
Well, the thing is that in this thing here, all the effort really is in solving the time harmonic problem. So I mean, it really comes down to what you need to do for that. And then basically you can if you have these functions f1, f2, and you know you can calculate them, and that way you can sort of figure out how you should sample your frequencies. So if you do it fully numerical from to begin with, it's quite sort of I don't really know how to compare, because it's difficult to compare. But the point is that you what is at least for water waves very nice about this method is for the time harmonic problems, very efficient methods have been developed and are still being developed, so you can really make use of these for this problem.
Okay, well, thank you again.